pretty basic. Shouldn't be too big of a deal. We're going to, again, focus on systems of equations, specifically now linear first-order equations, and we're going to talk about what form we want to have these in, which will lead into what we do at the end of the unit. But it all kind of stems down from this. You guys already know that ordinary differential equations can be written as isolate highest derivative. So let's say it's the nth order derivative. And then the rest would just then be a function of whatever independent variable we have and all the other derivatives. So y, y prime, y double prime, and so on, up to the n minus first derivative. So kind of along those lines, we're going to go with the fact that first order systems can be written in a pretty similar form, where we have one equation where we have one of the derivatives of the dependent variable isolated, and we do that for every dependent variable. We just isolate the derivative, leaving us with a function which we'll call g1, and then we'll have our dependent variable. And then if this is a system of equations with n equations, bless you, then you're going to possibly have all the non-derivative variables, so x1, x2, all the way up to x sub n, as the makeup of the function on the other side. And similarly, we can do that with the other ones. We should kind of mention that not all systems of differential equations are solvable. We're going to focus on the ones that we can actually solve, and the ones that have a specific format. So we're going to focus on the ones having what we call normal or canonical form. And this is essentially what we mean by normal form. When you actually write it all out, it's going to look something like this. dx1 dt equals, we'll go a11 of t times x1 plus a12 of t times x2, and so on, plus a1n of t times x sub n plus f1 of t. And then the following equation would be dx2 dt, and we're going to use the same kind of notation. Instead of 1, 1, we'll go a21. And if you know anything about matrices, you're starting to maybe see some of this notation look very familiar. So if we have a system of equations with n equations and n derivatives, it's going to look something like this. And just to tie into what we're going to do later, what do you suppose the notation A11, A2, 3, and all that stuff would mean? Row and column. Okay, so eventually we're going to tie this in the matrices, and that's why we're doing this notation now. Okay, good. So now here we have the coefficients and functions are continuous on a common interval I, so we're working with that assumption. And now when all the functions, we'll go f sub I of t, so we're talking about f1, f2, f3, all the way down to f sub n. When all those functions equal 0, we say the system is homogeneous. Otherwise, it's non-homogeneous. Okay. So all this is really in this section is manipulating the equations to get them kind of in this format here. Pretty basic. Also, we'll focus on, if we have a higher order equation, how to turn that one equation into a system of just linear equations where they're all first order derivatives. Okay, so we'll do a couple of examples like that so you guys get the idea. So let's write the differential equation 2y triple prime minus 6y double prime plus 4y prime plus y equals sine t as a system in normal form. Okay, and the method for doing so is actually pretty straightforward. First, we're going to isolate the highest order derivative. So y triple prime would be equal what? Move everything to the right. Minus 1/2 y minus 2y prime plus 3y double prime plus sine 1/2 sine t. Okay, so first isolate whatever the highest order derivative is. And now what we do is introduce some variables here. So we let y equal x1, we let y prime equal x2, and we let y double prime equal x3. Okay, so we're going to use this equation with these assumptions and go back to this format where we have first order derivative for each variable. So what we want to do is say what x1 prime is going to be, what x2 prime is going to be, and now what x3 prime is going to be. What would x1 prime be? Y prime, yes, which is x2. And then x2 prime is x3. And now x3 prime, we'd have to take the derivative here, which means we just want third order derivative of y, which we have here. So we're going to use this, but we're going to plug in all the x's instead of the y's. So we're going to have minus 1/2 what? What's y? x1 minus 2, y prime is x2. 3, y double prime is x3 plus 1/2 sine t. Okay? Questions? Pretty basic stuff. Okay, now the idea behind this is when you have this differential equation, ultimately what you want to know is what the solution for y is. You want to know what y of t equals, right? Well, it may be easier to actually treat it as a system where you can just find x1, x2, and x3 simultaneously. Okay, and if you know what x1, x2, and x3 are, well, not only do you know what y is, but you know what all the derivatives are as well. Okay, so that's kind of the use for taking a higher order equation, reducing it to a system of just linear equations. Okay, let's try this example. So we're going to take d squared minus d plus 5 times x plus 2d squared y equal to e of t, or e to the t, and then minus 2x plus d squared plus 2 times y equals 3t squared. Okay, so the idea here is, yes, we have a system of equations, but now currently it's a system of two equations, both are second order equations. Okay, so we're going to try to do the same kind of thing that we did earlier, reduce this to a system of equations where all the equations are just first order derivatives. Okay, so first we'll do the same kind of thing. We're going to isolate the highest order derivatives. So I'm going to get d squared x from the first equation, and I'll leave the 2d squared y on the left. And I'll get everything else on the right. So I'm isolating the second order derivatives and getting everything else on the right. So we're going to have e to the t, and I'm moving over the dx and the 5x. From the second equation, we just have one second order derivative, and that's just d squared y. And then again, I'll move everything else to the right. So 3t squared plus 2x minus 2y. And now what you want to do, we're going to use this one. This is good. But I also want to know exactly what d squared x is going to be. Okay, so just like earlier I wanted to know higher order derivative, here I'm done because I know exactly what d squared y is going to be. Here I want to know what d squared x is going to be. So what could I do with both of these equations to get an idea for that? So what is d squared x? So eliminate. So then we get d squared x. The two d squared y's go away. And then this is going to be e to the t minus 6t squared. Let's see, we're going to have x is minus 9x plus plus 4y plus dx. And we know what d squared y is. That was 3t squared plus 2x minus 2y. And we'll do something similar. We're going to introduce some variables. Since I already have x's in here, I'm going to say u. So I'm going to let dx equal u, and I'll say dy equal v. So now our system, we have four linear variables. We have x, we have y, we also have u and v now. So the system is now these first two, dx equals u, dy equals v. And now I want to know what du equals, and I want to know what dv equals. Okay, so we've reduced it from two equations of second order equations to four. These are all linear now, and it's just one order, a first order derivative here. So du, going back here, if u is dx, then what's du? Du would be d squared x. So d squared x is just going to be this. So I'll have, and I'll put it in the right form, minus 9x plus 4y plus, I don't want to use dx, I will use u. And we have e to the t minus 6t squared. And then similarly dv, if you look here, if v is dy, then dv will be d squared y, so I'm just using this equation here. And I'll get 2x minus 2y plus 3t squared. So here's another system in normal form that actually ties back to a system where we had second order equations. Okay, so both of these are the same thing, either that or this form. And again, there may be a practical purpose for getting everything into a first order equation. We'll start solving some of those pretty quickly. Okay. Any questions on this? Okay. One last scenario and we're done. So if you have questions on homework or you just want to work a little bit. If we're done really early, that's fine. So here's an example with a mixture problem. But now we have 2 tanks. And let's say we have coming in, we have water at 3 gallons a minute. Going out and into tank number 2, we have a mix of whatever we had in tank A at 4 gallons a minute. And now leaving B and going elsewhere is a mix of whatever's, and let's call these, I guess, tanks A and B then. A mix of leaving at 3 gallons a minute. And then let's also have some leaving B back into A. Why not? Whatever mix is in B at 1 gallon a minute. And here's what we know. A contains 50 gallons of water. And 25 pounds of salt. We like to use salt in this book, but really this could be any mixture. Are dissolved. B also contains 50 gallons of water. And that's pretty much all we know. So what do we want to do? We want to find a system of equations modeling this scenario where x1 is equal to the pounds of salt in A, and x2 is equal to the pounds of salt in B. So it's pretty, I mean, it's not hard. It's like the ones we did earlier. You just have 2 of them. So let's look at A first. I think this much should be clear. The rate of change of salt with respect to time is simply going to be the rate of salt coming in minus the rate of salt leaving. So let's figure out what's coming in. Maybe I'll write in, out. Coming in, we have 3 gallons per minute. But how much salt per gallon are we getting pumped in through there? 0 pounds per gallon. We also have, from tank B, we have a mix coming back into A. And that's coming in at 1 gallon a minute. And the concentration of salt would be what? X2 over 50, and that's pounds per gallon. Pretty simple. Out. All we have leaving is a mix at 4 gallons a minute, so 4 gallons a minute. And the salt there would be X1 over 50 pounds per gallon. So dx1 dt, if I calculate the in, you just get X2 over 50 minus the out, which is 4 times X1 over 50. We'll clean these up in a little bit, but that's dx1 dt, and we'll do the same exact thing for B. So for tank B, dx2 dt, again, will be equal to the rate of salt coming in minus the rate of salt going out. In, we have just the 1 coming in from A, so that's a mix at 4 gallons a minute. And what's the salt concentration there? From A, it would be X1 pounds of salt per 50 gallons. And that's it. Out, we have 2. We have a mix going elsewhere. We don't know where that's going. And then the mix going back into A. But out, we would have then the 3 gallons per minute. And that's going to be X2 over 50 pounds per gallon. And then we also have that 1 gallon going back into A. And that's also at X2 over 50 pounds of salt per 50 gallons. So dx2 dt, just simplify in, we have 4x1 over 50. Out, we have 3x2 over 50 plus 1x2 over 50, so that's minus 4x2 over 50. And now if we write these in the usual format, so in normal form, and let's go ahead and simplify. dx1 dt, dx2 dt. So dx1 was x2 over 50, so I'll put that here. And we had a negative, if we reduce the fraction, 2x1 over 25. And with dx2 dt, just reduce the fractions. 2x1 over 25 minus 2x2 over 25. Okay. So it's just a little bit of modeling with systems and putting things in the right format. That's really all that's in this section. So it should be pretty straightforward tonight. Tomorrow we'll start matrix theory. So if you're a little rusty on matrices, that would be good for you. And we'll finish that up on Friday.